We're going to start talking about chemical reactions now, and in particular we're going to focus on a dynamic view of what goes on in a reaction. Our learning goals are going to be to characterize reactions that are reversible and define characteristics that might represent a reaction at equilibrium. So chemical equilibrium. Can chemical reactions engage in a dynamic equilibrium? Well, we know they have to have certain necessary features. They need to have smaller mobile units, which in this case would be the reactants and products. It needs to be a closed system. Normally when we set up a reaction, there are a finite amount of materials available, so that's a closed system. The only thing that's left is to determine if there's reversible dynamics. Well, I want to draw a picture for you that is reminiscent of Module 3, and that's an energy diagram of a reaction where we've got reactants on the left and products on the right. Now, as we talked about at the end of that module, reactants are in a stable place, but if you add enough energy, they can get up over this hill, which is in fact the transition state, and get over to products. The real question, though, is at the top of that hill, is it only going one direction or can it go both directions? In other words, can we have both forward and reverse reactions? Well, in principle, it can do that. It can go in both directions, but it has to be a simple type of reaction, that is one that goes through only one transition state. So simple reactions that involve one step often are reversible because going one direction is no less favored than going the other. A more complex reaction that has to go over several of these, and combustion is a good example of this, typically are not reversible. So we have a case where, in the case of chemical reactions, sometimes it's reversible and sometimes it's not. Let's take a close look at a particular reaction. I'm going to look at the reaction of nitrogen monoxide with chlorine to form NoCl2. And what I want to do is take a look at how this reaction proceeds in time. So it means we need to define our starting points. I'm going to have starting conditions that represent the concentrations of NO and Cl2. In this case, they'd actually be partial pressures, but we'll call them concentrations. And I'm going to start with no product at the beginning. So we're just going to have reactant molecules present. So what I want to do now is generate a graph of what this reaction looks like if I were able to track each of the species in this reaction as it evolved in time. So I'm going to start with initial concentrations of each of these drawn on the left-hand column. And then we're going to see how they proceed as we allow time to evolve. Now I'm going to start by just looking at the two reactants. What would they look like if we were able to track them in time? Well, it turns out they would follow a curve that looks something like this. Now, I think it's pretty easy to understand what's going on at the beginning. As they're reacting, of course, they're going away. So they can't hang around if they're reacting and turning into NoCl2. But what we haven't anticipated is at long times that they kind of flatten out. They kind of hit a plateau region. What happens with the NoCl2? Well, it's just the opposite of those two. It's growing in with time, and like them, it flattens out as we go to long times. So there's some interesting things going on here, and we need to delve a little bit deeper to figure out what these are. Now, one observation I'd like to make is I want to draw lines across here that indicate where the initial concentrations of the two reactants is. Now I'm going to draw the distance between their initial concentration and the place where they leveled off. Okay, and I'm doing it for all three of these species. So for NO, for Cl2, and for NoCl2. Now if you look closely at these, they all look like they're equal. The gaps between where they started and where they ended are all equal. So why is this? Well, it turns out there's no big mystery with this. This is just reflecting the stoichiometry of the reaction. This is basically saying every time one NO molecule disappears, that means a Cl2 molecule had to disappear too. And when those two disappeared, one NoCl2 molecule was created. So in fact, all of these curves are really the same curve. The NO and the Cl2 are just shifted relative to one another. The NoCl2 curve is turned upside down. But that's what tells us that each of those things must be equal, because I'm giving up one molecule of NO and one molecule for Cl2 to make one molecule of NoCl2. But there's another question here that we haven't asked that is maybe even more puzzling. And that question is, why don't these decay to zero? Why doesn't it use up all of the limiting reactant in this case? Instead, we have not only that neither of the reactants goes to zero, But we also have the case that the NoCl2 levels off as well. They're all level at that point. Well, when they're not changing anymore with respect to time, that's a sign that there's something about it that is stable now. There's something about it that is an equilibrium. So let's talk about this a little bit more with respect to equilibrium. The explanation for this flat thing is that the reaction is reversible, which is to say we not only have this reaction happening where the two molecules are coming together to make NoCl2, but we also have some of this happening where the NoCl2 is breaking up to form NO and Cl2. So when we write this equation, we actually tend to write it with this double-headed arrow. This is a special notation that we use in chemistry to indicate that something is reversible, that it's going in both directions at the same time. So I'm going to change the header on the graph to reflect that. So now we've got NO and Cl2 in equilibrium with NoCl2 up at the top there. Now, the key for all of this is that this is what's explaining this big flat region out on the right-hand side of the graph. That is the place where equilibrium has occurred. It was not present earlier in the reaction when we had these two things sloping down from zero and NoCl2 sloping up from zero. It's only out there where it's flat because that's the place where the concentrations are no longer changing. So from a macroscopic observer, we no longer have any action going on. This is the case that represents a chemical equilibrium, which basically says that all the species are present in constant concentrations, but just because their concentration is constant doesn't mean that the reaction isn't still proceeding, some of them in the forward direction, some in the reverse direction, but they're balancing each other out.